this video, I will show intuitively why Routh-Hurwitz works. First, let's look at the following example. Here, the characteristic equation has roots at -2, -1, plus or minus j, and 1/2 plus or minus √3 over 2j. This is a marginally stable system. If we look at the roots table, we see that the first and second row form our characteristic equation. We can also consider the second and third row as a polynomial as well. If we interpolate between them, we can see that the roots move from the roots of the original polynomial to the next polynomial. Also note that the poles on the j omega axis are not moving at all. We see that one of the roots moved off to -infinity and disappeared, as the polynomial finally dropped rank. In general, as we interpolate between the polynomials, represented by the rows, the roots on the j omega axis never move, and the roots never cross the j omega axis. Thus, the stability of the reduced polynomial translates to the stability of the original polynomial if all the roots that went off to infinity indeed went to -infinity instead of plus infinity. So how do we know if the roots went to -infinity or positive infinity? Consider a degree n polynomial with roots p1, p2, all the way to pn. Then by expanding it, we get the following. Thus, the sum of the roots is -an-1 over an. As the leading coefficient goes to 0, the sum goes to -infinity if the two leading coefficients have the same sign, and positive infinity if they have different signs. We know that our other roots are finite, so if the vanishing root went to -infinity, we must have an and an-1 with the same sign. On the Routh-Hurwitz table, this means that the coefficients on the left have the same sign. Let's look at an example of an unstable system to demonstrate this. Here, going from row 1 to row 2, the leading coefficients have the same sign, so the root goes to -infinity. Now, going from row 2 to row 3, leading coefficients have different signs, so the root goes to positive infinity. Thus, Routh-Hurwitz maintains the information of stability of the system by sending the poles off to infinity one by one, while keeping track of which side of the plane they went off to by the change of signs. But when should we terminate? Obviously, we terminate at the end of the table. But if we have a row of zeros before we get to the end, as seen here, then our polynomial has only even exponents of s, indicating the roots are on the j omega axis. In this case, we know that the system is marginally stable. And this is how Routh-Hurwitz table